Okay, I'm recording, so that's good. So yeah, this is the captain speaking. We're going to go through the very last tutorial, all right, for my part of MA4002 Fluid Dynamics module. So for this very last module, all right, as I'm quite sure some of you guys are aware, we're dealing with turbomachinery. Okay, so there are 4 questions, and each question is unique in its own way. Okay, so let's run through the questions and see what all right, whether we are able to gain more understanding in terms of how to solve them, making use of the information that's made available to us in the questions. Okay, so for question 1, we have a centrifugal water pump. Okay, that's always good news because we know that, right, this must be a radar device, right, rather than an actual device. Okay, so we are told that we have a centrifugal water pump that has got an impeller diameter of 0.5 meters. So this impeller diameter, surely it must be the entire impeller. That means the OD, so as to speak. Okay, because there's a hole in the middle, right? Okay, but in this case, the way it describes is the impeller diameter. That means it's the external OD, all right? The external diameter rather than the diameter of the eye there. Yeah? So this diameter, the diameter of the impeller is 0.5 meters, and we're told that this water pump is actually operating at 900 RPM. Okay, we're told that the water enters the pump parallel to the pump shaft. Now, you guys might be wondering, what's the meaning of this statement? Okay, all right, this statement basically means that, all right, the velocity, the absolute velocity that's entering the impeller, all right, is such that all the entire velocity component is normal, in the normal direction. Okay, so it means that there's no tangential velocity, because if you think about it, if the water is parallel to the pump shaft, geometrically speaking, all right, if you guys can recall, if you guys can't recall, I highly recommend you guys go back to the lecture notes, see how the impeller, the schematics of the impeller, okay, and then basically try to relate the velocity triangle. Okay, you realize that if the velocity is parallel to the pump shaft and into the eye, before going to the impeller, that means there is no tangential velocity at the inlet. Okay, so that's what that statement is all about. Okay. Now, if the exit blade angle beta 2, so that's the exit blade angle. All right, if it's the inlet or entry blade angle, it will be beta 1. Okay, but we're told that, right? We are told that if the exit blade angle beta 2 is equals to 25 degrees, determine the shaft power required to turn the impeller when the flow through the pump, or the flow through the pump is 0.16 meter cube per second. Okay, last but not least, we're told that, all right, the blade height is uniform throughout, all right, from the inlet all the way to the outlet at 50 mm. Okay, so about 2 inches high. Okay, now once again, I highly encourage you guys when trying to solve problems, or it doesn't matter if it's for this module or any other module, to be honest, always list down the information that we're given, right, before we can try to. It's like crime scene investigation, you know. All right, before you can do anything, collect all information that they're able to get, right? So in this case, we're told that, right, these are the stuff that we're given. The diameter of the impeller is 0.5 meters. The angular velocity is 900 RPM, clearly. All right, we have to convert it to radians per second for our proper calculations later on. Beta 2 is given as 25 degrees, and the flow rate, Q, surely must be equal to 0.16 meter cube per second. Okay, now, if you realize that for this question, right, we're not told of any efficiency levels. Okay, so in this case, all right, what we're going to assume is that the shaft power, all right, P, all right, okay, we assume it to be equals to the work done on the fluid, okay, PW. That means we assume P equals to PW, all right, because efficiency is not provided. Let's assume it's 100% efficiency. Okay, now take a step backwards and ask ourselves, what do you mean by P? What is P? Right? P is nothing, all right, but the product of torque and angular velocity. Okay, and if we want to relate, okay, because if you think about it, right, this is the shaft power, isn't it? Okay, because the torque of the shaft, the angular velocity of the shaft, all right, clearly. But P, since we assume P equals to PW, by definition, P equals to PW equals to rho Q into U2 VT2 minus U1 VT1. So this formula, all right, okay, we've covered during the in the lecture slides. So I hope it's not too alien to you. Okay, it should look familiar to you. Okay. Now, as I've mentioned, since the water enters the pump parallel to the pump shaft, that means the entire flow absolute velocity component is in the normal direction. That means we only have Vn. There's no V. Sorry, we only have Vn1. There's no Vt2. Sorry, there's no Vt1. All right. 1 represents the inlet. 2 represents the outlet. All right. Just so we know, just so we're on the same page. Okay. So if the let me reiterate what I just mentioned. If water enters the centrifugal pump parallel to the pump shaft, it means that Vt1 equals to 0. There's only Vn1. Okay. If that's the case, actually it makes our life easier because equation 1 can be further simplified. All right, such that it becomes P equals to rho Q U2 Vt2. So that means for us to find out the shaft power, we just need to know the density of the fluid. In this case, is water. I'm quite sure you guys know the density of water, rho. The flow rate is actually given 0.16 meter cube per second. That means we only need to calculate U2 and Vt2 because these are the only unknowns. Okay, so long we're able to get U2 and Vt2, all right, we'll be set. Okay, now try to recall. Okay, go through a lecture slide. What are some of the formulas that we can come up with for Vt2? Incidentally, all right, we have got this expression, this relationship, which states that Vt2, all right, which states that Vt2 equals to U2 minus Vn2 cotangent beta 2. Okay, so we have U2 here, we have Vn2 here, all right, we have cotangent beta 2 here. Okay, so first thing first, let's try to find U2, the first term on the right hand side. What is U2? U2 is nothing but the tangential velocity, isn't it? Okay, at the axis. Now, we are given the angular velocity, of 900 RPM. If that's the case, all right, it should be simple enough for us, all right, to convert this 900 RPM to radians per second. We just have to multiply by 2 pi divided by 60. Okay, so take 900 multiplied by 2 pi divided by 60, and I'm quite sure you guys can get the angular velocity in radians per second. Okay, now to calculate the tangential velocity, please, all right. I'm quite sure you guys know what this relationship is all about. Tangential velocity is nothing but the radius multiplied by the angular velocity. So since we're interested in finding U2, so surely we must take R2 multiplied by omega. Okay, what's R2? R2 is nothing but the diameter of the impeller divided by 2. So surely it must be 0.25 because D is actually 0.5. Okay, so armed with all this information, surely you can multiply R2 with omega, okay, in radians per second. Once you've done that, U2, all right, can be found out to be about 23.6 meters per second. Fantastic, because this will be the first unknown that we managed to find. Remember this? So we managed to find this. So the last thing that we need to find is Vt2. Okay, now, as we've seen from equation 2, okay, all right, we managed to find U2, all right, now we need to find Vn2, okay, because beta 2 is given. So Vn2 is really the only unknown that we need to find before we can solve for Vt2. Thankfully, there is another relationship that relates the flow rate, all right, with Vn2. And if you think about it, this will be the right relationship to use because we are given the flow rate Q. Okay, so if you think about it, okay, at the outlet, Q equals to 2 pi R2 B2 Vn2. This is actually a statement of mass continuity if you think about it. Okay, because flow rate Q is nothing but the circumference at the outlet, 2 pi R. Remember the circumference of the outlet, 2 pi R, multiplied by the height of the blade, okay, B2. Okay, that's going to give you the cylindrical surface area. Okay, and then if you multiply by the Vm, the normal velocity component that's coming out from this cylindrical surface, surely it must be equal to flow rate. It's a bit like potential flow, isn't it? It's a bit like sauce, except that in this case we have got a blade height, if you think about it. In fact, that's the only difference, right? Can you guys see the relation, see the similarity, or roughly, you know, the similarity between this relationship and the source for potential flow? Right? The only difference is we have got extra B here. Okay, but anyway, formally speaking, we know that Q is defined as 2 pi R2 B2 Vn2. We know what's R2, we know what's B2, we know what's Q. Surely we can find Vn2. And Vn2 is about 2.04 meters per second. So now that we know Vn2, surely we have all the necessary information all right, to plug into equation 2, and for us to find VT2. And VT2, all right, will be about 19.2 meters per second once you work things out. So that's the second unknown for this expression. So we've got U2, we got VT2, we know what's Q, we can surely assume that the density for water. So chuck all this stuff onto the right hand side of here, and you guys can work out, all right, the shaft power that's required. It will work out to be about 72.4 kilowatts. Okay, all right. So the very first question is a very, very classical centrifugal water pump. Okay, question. Of course, things are slightly simpler because we are assuming highly idealized, okay, flow entry conditions whereby you don't have to worry about beta 1 and so on and so forth. Okay, all right. But still, as a first question, I thought it's a nice entry question, yeah? Okay. Let's move on to question 2. Okay. Question 2, we're no longer dealing with centrifugal pump. We're talking about the actual pump. Okay, so surely some things will be different. Surely the assumptions and the formulas and the way that the flow actually flows through an actual flow pump is going to be different from one that is flowing through a radial flow device, right? The radial centrifugal pump. Okay, so for this question, we're told that we've got an actual flow pump. It's got a stator blade. A stator blade means that it is it's a stator, meaning you still have the hub in the middle, and you still have got all those blades. But these blades are not spinning; they are static. That's why it's called a stator. Okay, all right. So we have got a stator blade that's positioned upstream of the impeller. So the impeller will be the one that is basically the rotor. Okay. So we have a stator blade positioned upstream of the impeller or rotor, and this stator blade, okay, provides an angle alpha 1 equals to 60 degrees, okay, to the flow. So alpha 1, okay, is the flow angle, all right, for the absolute velocity v. Okay, in this case, alpha 1, right, since we're told that alpha 1 equals 60 degrees, that means v1, all right, is making an angle of 60 degrees, all right, relative to the flow. Okay. Now, the radius of the impeller tip is 285 mm. Okay, so that means the rotor. Okay, all right. Basically the outer radius, if you will. Okay, is 285 mm, and the hub radius is 135 mm. So if you think about it, the hub radius is probably that's the inner radius, right? One we have an external radius, sorry, the outer radius and the inner radius. Okay, because the blades are fixed on the hub. So that means the blade starts from R1 equals to 135 mm all the way to R2, 285 mm. Okay, the blade can't commit. Basically, you can't have a zero hub situation, isn't it? There's nothing to hold the blade. And so there must be a hub radius. It's just a matter of how big or how small. Now, determine the average blade angle at the impeller axis, right, or the rotor axis. If the flow rate is known to be 0.57 meter cube per second, and that the theoretical head is 2.85 meters, the rotational speed is 1500 RPM. Okay, I know this sounds a bit confusing here and there, especially let's say this is the first time we're dealing with machinery. Okay, but like I said, the easiest thing to do, all right, or the best way to go about doing this is to list out the stuff you are given with the correct nomenclatures. That will make things a lot clearer. If nothing else, you can at least figure out which formulas we can use. Okay, so now Ri, that's the inner radius, okay, it's given as 0.135 meters. I converted to meters as a unit, right? Ro, that means the outer radius, okay, we know that it's actually equals to 0.285 meters. Alpha 1, okay, is equals to 60 degrees, is given by the question. The flow rate Q, all right, is 0.57 meter cube per second. The pressure head, all right, the theoretical pressure head, H, is 2.85 meters. Angular velocity is 1500 RPM. Okay, we're asked to find, all right, beta 2, because that's the average blade angle at the axis. All right, so if you think about it, okay, the blade angle, all right, at the inlet is beta 1, so the blade angle at the exit will be beta 2. Okay. Now, there's a few assumptions we have to make, okay, because the question did not say either way. So the first assumption we have to make is that the relative velocity component, all right, W1, okay, that means at the inlet is parallel to the rotor's leading edge. Okay, this is just to say that, all right, this idealized condition is pretty much like in question 1, whereby we're told that the water actually enters parallel to the pump shaft. Okay, I mean, to be honest, we don't need to make this assumption to still be able to solve the questions, but you know, just to make sure that everything is so-called is confirmed to be idealized, so as to speak. Now, it will be useful if we were to sketch the velocity triangle for the rotor. So this is the rotor blade, and let's say that it's moving from left to right with a certain angular velocity. Okay. Now we can draw the velocity triangle at the inlet. Okay, when the flow flows, just when the flow is about to flow along the blade, and we can also draw the velocity triangle at the exit. Okay, I'm quite sure once you draw this triangle, okay, you must be thinking, so which one should I draw first? Always draw W first, because you know that W, okay, for idealized situation, which will assume most of the time, not all the time, but most of the time, W1, we always want it to be parallel to the leading edge of the rotor blade. And W2, we always want it to be parallel or tangential to the axis, the trailing edge. Okay, so always draw W1 first. That one's the easiest one. Okay, W1, W2, because we know what are the conditions. Okay, next you should draw, all right, the tangential velocity. Sorry, not the tangential velocity, the blade velocity, U. So in this case, U1 and U2. All right, but in this case, U1 equals to U2 because the entire blade is rotating at the same time. Okay, at the average blade angle, at the average blade radius there. So U1, that's the reason why I put U1 here and U1 here, because even if I put U2, it's the same as U1. Okay, all right. So yeah, after that, once you have U1, you have W1, you have U2 and W2, you can surely draw V1 and V2, and that will complete the velocity triangle. And after that, you can basically draw the Vn component like Vn1 and Vn2. Okay, and after you fill up basically indicate the alpha 1, beta 1, alpha 2, beta 2. And basically that will sort of like give you a good idea how the velocity triangles look like. Okay, and to construct the equation. Okay, now sometimes it is possible, all right, to solve the questions without any knowledge, without sketching the velocity triangles. Okay, during in exams, hang on, Barry. Yeah, let me just say, in exams, all right, it's not compulsory to draw velocity triangles if you ever encounter, all right, a turbomachinery question. If you understood the equations, all right, and how they're formulated and how you could use them, there's no need to draw velocity triangles if you don't want to. Okay, all right. If you are sure about the principles, all right, that's fine. Okay, all right. Unless the question says that, look, please draw the velocity triangle, and then there's some marks attached to it, then you know you have to draw, right? But if let's say there's no requirement for you to draw, it's not explicitly stated, there's no need to draw. Okay. Now let me go back to the question. So Barry asked a question, if the blade you drew is in the opposite direction, the calculation shouldn't change. No, it shouldn't change. Okay, it shouldn't change. All right, if you understood the principles clearly, it will not change at all. Okay. Okay, let's proceed to solve the problem. Okay, so now this is an axial flow problem. Okay, we know that for axial flow devices, U1 equals to U2 equals to U because the entire blade is spinning at the same omega. All right. Okay. And if you think about it, Vn1 must be equals to Vn2. And since they're the same, why don't we just call it Vn? Right. The same way why we let U1 equals to U2 equals to U. They're the same. Okay. And once you are clear upon it, all right, we can actually proceed to solve the question. Solving this question is actually quite simple procedure-wise. Okay. Because now, if you think about it, we need to find beta 2. Okay, and if you go to the lecture slide, okay, there is one equation, all right, okay, that will allow us to relate beta 2 with the other flow parameters or geometrical details, all right, that we're provided with. That's why I say, see, that's why I always say, it's very useful to list out the stuff that you're given here, because then and only then will you be able to figure out which formula to use. Okay, because you see, well, I know what's H because it's given by the question. U is something that certainly I can calculate. Vn I know is something I can calculate as well. I'm given alpha 1, and so on and so forth. Okay, so if you think about it, okay, I just have to calculate a few stuff, all right, chuck it in, combine with the information that we're given, and we can proceed to solve this equation for beta 2. But first thing first, okay, take a look at this expression, all right, GH is nothing but U squared minus U Vn into cotangent alpha 1 plus cotangent beta 2. Okay, so now, once we have this, just have to ask ourselves, do we have H? Yes, we have got H. Do we have U? If we don't have U, then we calculate what's U. All right, another thing that we need to calculate will be Vn. Okay, Vn, to calculate Vn is quite simple, because if you think about it, Vn, the normal velocity passing through the rotor, is nothing but the flow rate divided by the effective cross-sectional area of the rotor, right, through which the flow must flow through. Think about it, the rotor has got a hub. So the hub is actually blocking the flow, isn't it? So we need to find out the area, right, the cross-sectional area of the, based on the impeller's external radius or outer radius, minus the cross-sectional area of the hub, because the hub is blocking the flow. So if you think about it, Vn is nothing but the flow rate divided by pi into R naught squared minus, not R naught, Ro squared minus Ri squared. Because that means that the denominator will be the effective cross-sectional area. We know what's Q, and surely we can work this thing out because we know what's Ro and Ri as well. And Vn can be worked out to be about 2.88 meters per second. Okay, so voila, one unknown down. The next unknown we have to calculate is U. What's U? U, if you think about it, is nothing but, right, the radius multiplied by the angular velocity. Okay, and in this case, since, all right, we read this question carefully, all right, okay, we're asked to determine the average blade angle at the impeller axis. So in this case, let's assume, okay, all right, that the average blade angle at the average exit blade angle happens at the average radius location. So in that case, I can make use of this relationship. U equals to the product of the average radius of the rotor multiplied by the angular velocity omega. Okay, the average radius of the rotor is nothing but Ro plus Ri. That means the outer radius plus the inner radius divided by 2. Of course, these are just a rough estimation. Okay, all right. Once we found out what's R average, we can just basically multiply by omega. But of course, please make sure you multiply 1500 by 2 pi divided by 60 so as to get radians per second. And U can be worked out to be 33 meters per second. So voila, we have got all the quantities that we need to chuck into equation 1 to solve for beta 2. Okay, so I'm going to skip the workings. All right, you guys can do the workings yourself. Okay, I'm quite sure it's something that you guys are capable of. Just make sure you know just what exactly cotangent function is. Okay, some of you guys actually got confused. Okay, all right, just Google. All right, I'm quite sure you guys know. All right, or your calculator. Please make sure you know how to use a calculator to calculate all these cotangents. All right, so it can be worked out that beta 2 is nothing but 5.4 degrees. Well, which is awfully small, actually, if you think about it. Okay, awfully small. All right. Okay, so that will be all for question 2. Okay, question 3 is a fun question. All right, question 3 is a fun question. I think you're sharing your screen, I think. Could it be? Accidentally, I think. Yeah. All right, anyway. Yeah. So question 3 is a question that involves a Pelton wheel. Okay, and this question seems to be quite a fun one because, as you will see later on, I have this strong feeling Pelton wheels are easier, so as to speak, quote unquote, because at least it's easier to visualize. You know, you can always, when it comes to Pelton wheel, just imagine it's like a windmill, right? Okay, or a water mill. Actually, it should be a water mill. All right, where the flow of the water keeps spinning this wheel and hence producing torque and so on and so forth, isn't it? Okay. Now, let's take a closer look at question 3. We've got a Pelton wheel. Okay, let's say shown schematic here, part of my drawing. Looks I don't know whether it looks like a Pelton wheel or looks like a bloody sunflower. All right, we have a Pelton wheel that has got a diameter of 2 meters, let's say. Yeah, okay. We're told that it develops 500 kilowatts of power when rotating at 180 RPM. Okay. Now, what is the average force of the water that's hitting against the blade? So let's call the force, the average force F. Now, if the turbine is operating at maximum efficiency, I think this is something that we kept harping about in the lecture. Determine the speed of the water jet from the nozzle. That means VJ, okay, VJ. And secondly, the mass flow rate of the water. Okay, I believe I've covered Pelton wheel and turbines and so on and so forth in the third part of my recorded video. Okay, so I hope you guys have watched that. Okay. So now again, let's put down what we are given. Right, the diameter of the Pelton wheel is 2 meters. The power that it develops is 500 kilowatts. Right, the angular velocity is 180 RPM. Surely we have to convert it to radius per second later on. Okay. First thing first, we are asked to find the average force of the water that's hitting against the blades. If you think about it, the force, all right, must be what's spinning the Pelton wheel. And in spinning the Pelton wheel, the Pelton wheel must develop a torque. Okay, so finding torque is important, right? Because it allows us to find out how to relate to force. Okay, now by definition, first thing first, you can notice we're given the power developed. Okay, power developed, if you think about it, by a spinning shaft or spinning device or spinning wheel in this case. Power, all right, is nothing but the product of torque and angular velocity, P omega. Torque by a spinning device is nothing but what? Torque is a moment. Torque is a moment quantity. So for a moment, surely, all right, in this case, torque can be defined as a force. In this case, will be the force that's acting upon the blades, multiplied by the moment arm. In this case, all right, the moment arm of this Pelton wheel. So if you think about it, force F, this is what we want to find. And the moment arm, if you think about it, is the distance from what, the center of the Pelton wheel all the way to the diameter of the Pelton wheel, because the blades would have been attached at the tip of the Pelton wheel's external outer diameter. All right, so that means the moment arm must be equals to the radius of the Pelton wheel. Radius, of course, is defined as d/2. So this is the formulation for torque, and we are interested in finding out what's F. Okay, so we can make use of this formulation to help us to find D, because you think about it, on the left-hand side is P, power. What's power? It's given as 500 kilowatts. So you can take 500 times 10 to the power 3, okay, because it's kilowatts, equals to F, okay? F is what we want to find, multiplied by what? The radius. Radius is 2 meters divided by 2, because 2 meters is the diameter, and then multiplied by what? The angular velocity. So 180 RPM multiplied by 2 pi divided by 60. So, all right, clearly, F is the only unknown, and I'm quite sure you guys will be able to shuffle the terms around, punch the numbers into the calculators, and work out the F. It's about 26.6 kilonewtons. Okay, all right. Now, next, we're asked to find the speed of the water jet, okay, when the turbine is operating at maximum efficiency. Okay, now, power of a Pelton wheel, in this case, is defined as such. P equals to rho Q, U into Vj minus U to 1 minus cosine beta. U, all right, is the tangential velocity of the Pelton wheel. Vj will be the water jet velocity. Beta will be the blade angle, all right, that's associated with the Pelton wheel blade. Okay. We know that, all right, for maximum power, all right, beta must be equals to 180 degrees, and U must be equals to half of the jet velocity. So all this stuff, all right, we've covered in our recorded lecture previously. All right, so if you have no idea what I'm talking about, please go back and watch those lectures, okay? Now, since U is the tangential velocity of the wheel, surely it will be easy for us to find out what's U. Because if we're able to find U, surely we'll be able to find Vj, right? Okay, let's find out what's U, okay? All right, if you're able to find out what's U, think about it. if U equals to D over 2 equals omega, that means I can equate the right-hand side of here, right, to the left-hand side here, shuffle the terms around, and I can get Vj equals to D omega. Okay, all right. If that's the case, we know that D equals to 2 meters, omega is 180 RPM. We can multiply by, in fact, we must multiply by 2 pi divided by 60 to get radius per second. And we can get the jet velocity, all right, to be about 37.6 meters per second. Okay. So the last one is probably the one that most people trip up, the mass fluid. Because you're like, how can I relate to mass fluid? Think about it. The power, right, that's produced by the Pelton wheel, but surely, right, must be associated to the kinetic energy of the water jet. Okay. In fact, power is defined as the what? As half times the mass fluid m dot times the water jet velocity squared. All right. Okay. It's the rate of kinetic energy that's being transferred from the water jet to the blade, if you think about it. Okay. If that's the case, since we know what's the power that we're going to get from this Pelton wheel, we know what's Vj that we just calculated to be 7.6 meters per second in the first place. Shuffle the terms around. Okay, m dot is nothing but 2p divided by Vj squared. All right. We know what's p. We just calculated what's our Vj. All right, so plug the numbers in. All right, and m dot, the mass flow rate, can be estimated to be about 707 kg per second. Okay, that's all to it. All right, that's why I said Pelton wheel questions are typically quite interesting because it's something that we can easily visualize, and you know, and Pelton wheels, to be honest. Okay, a lot of questions revolves around situations whereby they're operating at the maximum efficiency. You know what I'm trying to say? Because once it's operating at the maximum efficiency, a lot of things, a lot of rules have been worked out for us. Okay, I think there's a question coming from a student, right? Tins, yeah, Tanasvaran. If we apply power equals to force times effective velocity, isn't it conceptually correct? I think you can try. I think it's conceptually correct because power is FV, isn't it? Try it out and see what happens. Okay, try it and see what happens. Yeah. Oh, hang on. Let me scroll down. Oh, you managed to get the same answer for force. Yeah. Why not? Okay. Yeah. That's the good thing about physics, right? And science. Things are consistent. Okay. So yeah, Tinasvaran, please go ahead. All right. That's fine as well. Okay. Okay, let's move on to the last question. The last question, okay, if you think about it, right? The last question must be something different from the first three questions. All right, just to recap, our first question, we have centrifugal pump. For our second question, we have an axial pump. For third question, we have got a Pelton wheel. Okay, and for the fourth question, if you have read the question, it's basically a turbine. Okay, it's actually a turbine. Okay, so a turbine is different from a pump, right? If you think about it. Okay, pumps are, we make use of pumps to basically increase, all right, the energy to the fluid that's been running, that's running through the pump. For question 3 and question 4, clearly we are talking about turbines. All right, for question 4, it's not a Pelton wheel based turbine. It's not a reaction turbine. It's a one. All right, it's an axial flow turbine, right, with blades. Okay, so as you can see, all right, so that's the clear distinction. Okay, hang on, I'm gonna cough. I'm sorry about that. Okay, all right, let's take a quick look at question 4. Okay, question 4 is a bit confusing because there are some. Yes, I'm okay. Thanks very much, Singer. Probably my coffee. Yeah, thanks very much. Now for question 4, things may be a little bit confusing because there are some technical terms that we use to describe the certain features of the turbines. Okay, so just bear with me. Okay, and I'll explain why. I'll explain what these terms are. For the question, let's run through the question. Water is supplied to an axial flow turbine under a total height of 35 meters. That means that's the pressure height, right? H. In fact, we can just say that, look, H is 35 meters. Okay. We're told that the mean diameter of the runner is 2 meters and it rotates at 145 RPM. Okay. Runner is basically the turbine blade. All right, it's okay. I think it's just an old-fashioned term. Okay, why do we call turbine blades runner blade? Because you know what? When water hits it, it runs around. Okay, all right. I know it sounds silly, like what's it called, pressure. It's some traditional terms, nomenclatures that we picked up, over the years and things like that. Okay, so you can read this statement as equivalent to the mean diameter of the turbine blades is 2 meters and the turbine blade rotates at 145 RPM. Water leaves the guide vane. This is the guide vane. This is not the turbine blade. So for turbine blades, okay, if you check some of the textbooks, okay, the turbine blades, some of these turbine blades, all right, they have got guide vanes before them, in front of them, a bit like stators, just to guide the flow nicely. Or such that the water will flow along the turbine blades, nice and smooth. So in this case, water leaves, you can read as water leaves the guide vane that's located upstream at 30 degrees relative to the direction of the turbine blade rotation direction. And the angle of the runner / turbine blade is 28 degrees at mean radius. If 7% of the total head is lost in the casing and guide vanes, that means all these are mechanical losses, right? And the relative velocity is reduced by 8%. Relative velocity, which component are we talking about? Is it W? Is it V? Is it U? It's W, right? Remember, W, all right, is relative velocity. V is absolute velocity. U is blade velocity. Okay, you have to get all this right, yeah? So we're told that the relative velocity is reduced by 8% due to friction in the runner. Okay, determine the blade angle at the inlet. Located at, we can assume that we take it at the mean radius location. Because why is this assumption necessary? Because you know why? The blade angle actually will vary, all right, from the root of the blade to the tip of the blade. Okay, it's very rare, right, for efficient energy extraction that the blade angle remains constant. But in this case, we'll say that I think we're trying to simplify the problem a little bit, or the problem is trying to simplify things a little bit. Just assume that we take the location at the mean radius location and determine the blade angle at that point, okay, at the inlet, as well as the hydraulic efficiency of the turbine. Okay, again, let's list out what we have. I always find it the easiest, and to draw the velocity diagrams and things. Okay, by given h equals to 35 meters, d equals to 2 meters, that's the mean diameter. Okay, and omega is 145 RPM. Now, if you draw the velocity triangles of a turbine blade, you realize that it's going to be a little bit different from that associated with centrifugal pump or an axial pump. Okay, the velocity triangle at the outlet will still resemble, all right, quite similar, resemble much like what we've seen for the centrifugal pump and the axial pump. Okay, but the inlet, you've got to be careful. The inlet will look a little bit different. Okay, the inlet will look a bit different because you know what? This is the turbine, so water should flow along the right below the curved blade, not on top of the curved blade. Right? Now let me just scroll out a little bit. Oh, okay. Now this is the actual flow pump. Look at this. W1 is flowing along the top. Right? It has got to be parallel to the leading edge, so it comes in this way. Okay. For a turbine blade, right? Look at this W1. It's flowing below the curved surface because for a turbine, the water is supposed to impart its energy by pushing the blade. Okay, so that's why W1 is in this direction, below the blade. Okay, and armed with U1 in this direction, our V1 will be here. Okay, but of course these are velocity triangles. All right, later you guys can move the vectors around. But I just want to make sure that you guys will not be confused or bewildered, by all these changes. Okay, so this will be a W1, this will be a U1 because the whole turbine, the blade, right, rotates at the same tangential velocity, blade velocity, and this will be your V1. And we're told of that we're given this alpha 1. Okay, all right, equals to 30 degrees because the water leaves the guide in at 30 degrees relative to the direction of the runner blade rotation angle. So this will be 30 degrees. This is basically alpha 1. Okay. Now, so once you constructed the velocity triangle at the inlet, let's consider the velocity triangle at the outlet. Thankfully, the velocity triangle at the outlet, all right, resembles more of what we encountered before. Okay. All right, because blade leaving the water leaving the blade is the same for pumps or turbines. Okay, it's only the inlet is different. But over here, we have a much more normal velocity triangle. Surely W2 must be parallel to the trailing edge of this blade. And this surely must be our U2. This will be our V2. Okay. Now, we're given, all right, this angle. All right. We're given this angle over here, which is 28 degrees. All right, because that's the angle of the runner blade at the mean radius. Okay. Right. So that's our, that's our beta 2. Okay. So as you can see, what do we learn from this? By when we sketch this and construct the velocity triangle and trying to figure out which angle they're talking about, and so on and so forth. I think a lesson, all right, can be learned here. That means you have to visualize the blades well. I think that's what it's all about. So I know that if you guys recall from my lecture slide, I slapped in a lot of the diagrams here and there. Please don't ignore those diagrams. Okay, please don't ignore those diagrams. I know sometimes you guys just go through the formulas and say that, okay, that's it. All right, I'm done with the lecture slide. Without going through the figure. So I will say that please, all right, focus on the figures. Okay, because from the figures, when you understand how these formulas are constructed, then we don't pull these equations out from our arse, okay, from nowhere. Okay, all right, they are derived based on engineering principles. Okay, so sometimes, right, you will appreciate the equations, the formulas a lot more, and you know their constraints and you know their limitations if you know how they have been derived. Okay, and you get a much better appreciation of the questions if you're able to draw the velocity triangles. Yes, I said earlier on, you don't have to draw if you don't have to unless you've been asked, but still sometimes if you are hitting a wall, all right, simply because you just want to use a formula and solve it, but yet let's say you couldn't, then in that case, sketching out the velocity triangles, all right, and understanding the principles actually helps you guys out. All right. Okay, coming back to this, I don't want to drag on for too long for the first hour. Okay, so this is what we have. Okay, first thing first, like I said, all right, because the entire turbine blade is spinning at the same time, so U1 surely must be equal to U2. Okay, and let's find out what's our U1 and U2. U1 and U2, if you think about it, are the tangential velocities. So basically, it's the product of the radius multiplied by the angular velocity. We know the diameter, so finding out the radius is not a problem. We know what's the omega in RPM. Surely, converting to a radius per second is not a problem. And we can work out U1 equals to U2 equals to 15.2 meters per second. Okay, so now, this question is very interesting because you know why? Because of a couple of statements for this. If 7% of the total head is lost in the casing and guide blades, so that means 35 meters per second. This 35 meter pressure head is not the one that you should be using for the calculations. Okay, because, all right, there's 7% loss. So if you think about it, that means we have to calculate the actual pressure head that's been transferred to the turbine blades by the water. So let's just call it H net, the net pressure head. Because we know that the 7% loss, so that means we have to take 0.93 and multiply by the 35 meters. All right. And that will give us 32.6 meters. So 32.6 meters will be the one that is, all right, after the losses, after the mechanical losses. actually. All right. Now we know that, okay, this is probably something that you guys have to think about it. Okay, it's not something to appreciate. It's not something difficult to appreciate, but does require a bit of the work. It does require a jump. It's a bit like powder and wheel. Okay, think about it. The net pressure hit, H net, right, must come from the what? Right, the water pressure hit. Okay, and if you think about it, if you go back to the energy balance equations, we know that H, the pressure hit, is nothing but the kinematic pressure hit divided by 2g. Sorry, the velocity squared divided by 2g. Okay, we don't consider any gravitational potential hit gain and so on and so forth. Okay, if that's the case, right, since we know that H net is reduced 0.6 meters, okay, that means it allows us to calculate what's our V1, okay, based on this number. Once you calculate our V1, which equates to 25.3 meters per second, then we can basically consider the velocity triangles. Okay, let's consider the inlet velocity triangles. Okay, I believe some of these expressions are already in your lecture slide, but if let's say if you look at the inlet velocity triangle, these are some of the relationships that you can strike out. Okay, now before we lose what we're supposed to find, let's go back to the question. What are we supposed to find? We're asked to find two things: the blade angle at the inlet and the hydraulic efficiency of the turbine. What is blade angle at the inlet? That's beta 1. Okay, that means we are supposed to find beta 1. Okay, now if you refer to the inlet velocity triangles, we can express W1 sine beta 1 equals to Vn1. And we know that W1 cosine beta 1 plus U1 equals to V1 cosine alpha 1. Okay, I'm quite sure you guys can see some similar terms. In fact, I can solve them simultaneously. All right, by making use of the information here, plug them in, and you will be basically trying to find what's W1. Because once you know what's W1, you can find beta 1. Okay, and beta 1 can be found out to be about 62.2 degrees. Yeah, the reasons why I don't want to go through details because I want you guys to go through to work out the details. Okay, because I know that some of you guys, unfortunately, maybe not you, all right, but I do realize that some students are still reading solutions of the tutorials. Okay, and the tendency gets higher once the solutions are very, very detailed. Okay, so this is one of the reasons why for some questions I skip the details because I want you guys, even if I upload all these solutions later on, you guys will feel like solving it because the details are not there. Okay. Now we found out what's beta 1, 62.2 degrees. Okay, now we have to find out the efficiency. Okay, all right, the hydraulic efficiency. Okay, now to find out the hydraulic efficiency, okay, we have to find out what's the pressure hit at the exit because we do know what's the pressure hit available at the inlet. Okay, now the pressure hit at the exit, to calculate the pressure hit at the exit, we have to make use of this formula. All right, okay, it's nothing but quite similar to this actually. Okay, but to calculate the pressure hit at the exit, we have to make use of this relationship. H at the exit is nothing but what? U2 divided by G to VT1 minus VT2. Okay, that begs the question, isn't it? What is VT1 and VT2? How do you get VT1 and VT2? VT1 and VT2 can be obtained if you guys basically establish relationships between the various different velocity components like this. Okay, so I skip the details because I think it's good practice. Okay, but you guys are supposed to make use of the outlet velocity triangles. Okay, construct equations or relationship that involves VT1 and VT2. Okay, all right, and solve for VT1 and VT2. So I think this is something that I want you guys to have a try. So I'll just show the results here so that you guys know the intermediate results and know that you guys are on the right track. Okay, but I want you guys to try. Okay. Now, once you know what's VT1 and VT2, in this case, VT2 is about 3.6 meters per second, VT1 is 21.9 meters per second. Chucking them all in here, and surely you know what's U2, right? Because U is the same. Okay, you can find out that the pressure here at the exit is 28.4 meters. Okay, and the hydraulic efficiency is nothing but this can be found out by taking this 28.4 meters divided by, right, the theoretical heat, all right, okay, the theoretical total heat, okay, that the water is supposed to have, okay. So take 28.4 divided by 35, and the hydraulic efficiency can be estimated to be about 81.1%, okay. And that's going to do it for tutorial 4, okay. Now, again, like I said, you realize that for question 1, all right, a lot of details are in the solution. Tutorial 2, I hold back a little bit. Sorry, not tutorial 2, question 2, I hold back a little bit. Okay, because I think this is simple math. This is something that you guys should be able to handle, because I really don't want to cultivate a habit of students just going through my detailed calculations and think that that's it, so simple. Okay, work it out, work things out by yourself, right? So that you have a feel for just how simple / difficult, right, the workings may be. And for question 3, there's nothing much to it. But you realize that for question 4, okay, same thing. I left out the detailed workings. You guys should know how to solve simultaneous equations and so on and so forth. Okay. Hand holding is fine, but I have to let go of your hand at some point. Okay, I think this is what I'm trying to do here. Okay. But I do provide a few of these paddings, so I have to speak just in case you fall. Okay, so there are still some intermediate answers here for you to towards to double check your approach. Okay. So I think, yeah, that's going to do it for us. Okay. And I think it's just nice. It's what, 11:27, about half 11. Yeah. Let's do what we always do. Let's go for a break. Come back about 10, 15 minutes later. All right. Stretch your legs, grab a water, go to the washroom. I don't know, chit-chat with your boyfriend / girlfriend. All right. We'll come back for the brief review. Okay. All right. So thanks very much. Okay. Let me just stop the recording.